In video 34 of the Foundations of Computational Economics course, we will look at numerical integration, in particular quadrature rules, and also we'll talk about Monte Carlo integration. So, as you would imagine, integration is all over economics. We will be primarily interested in stochastic elements in dynamic economic models, so integrating the expected future value function, but more generally expected discounted utility, discounted profits in models like that, or simpler. Bayesian posterior is the standard integration task, not only in econometric applications, but also in, for example, models of learning. Now, likelihood function with unobservables requires integrating these unobservables out, which is also often done by numerical methods. And then, of course, as many things, analytical solutions may not exist. So in order to proceed further, we need to learn how to compute numerical integrals. So as I mentioned, there are two main approaches, Monte Carlo integration and quadrature. And we will look at both of them in this video. Monte Carlo integration is a stochastic algorithm which is based on some draws from particular distributions, right? It's based on random variables to calculate a definite integral. Whereas quadrature integration is based on quadrature points, which have to do with function approximation effectively. So it's very good if you've seen video 31 on functional approximation. And so quadrature integration is based on fixed points and weights that create weighted sums of values of the functions at different nodes, right? Different fixed points. So we'll look at quadrature integration first, and then in the second half of the video, we'll return to Monte Carlo integration. The first step is Newton-Cotes formulas, with the goal of a definite integral between a and b of some known function f of x. The idea is very simple. We approximate the function somehow with some low-degree polynomials, and then integrate the approximation. So we calculate the integral of a very easy function, which represents our function of interest. And here we can, depending on the degree of the polynomial, we can have, first order just a constant, 0th degree. The constant could be just at midpoint between a and b, or function values of a and b. So, instead of integrating our function of interest, we just take a square of the rectangle. And that's, of course, a very crude approximation. Now, second order polynomial is a linear approximation, and we would derive a trapezoid rule, which basically calculates the area of the trapeze, right? Defined by the two consecutive nodes and the function values at those nodes. The third order polynomial quadratic approximation of the function will result in a Simpson rule. Right. So all of this, this approach can be thought of as being applied to the whole integral from a to b. And here, for example, we're seeing the Simpson's rule example. This is where we have 3 points on the integral a and b. Let me draw some points. Right, and we need a third point in order to fit a parabola to these 3 points where we calculate the value of the function. And then we integrate, the integral becomes this area here, the area in the red closed shape. With the trapezoid rule, right, we would only require 2 points and calculate the area of this figure. And with the linear function or linear constant approximation, the approximation would just give us a rectangle. Now, of course, we can do that for the whole interval of integration from a to b, but it would make a lot more sense to add points, right, and do this rules, for example, Simpson rules, in a composite way, which basically means that we want to separate, break out the whole a to b interval into sub-intervals and apply the rule on subintervals. And then, of course, it becomes more accurate, and even the constant approximation may start making sense if we have enough, large enough number of grid points. So here's the composite Newton codes rules. It's a collection of rules, right, depending on the approximation that we use. The idea is that we perform the same approach on the grid separately on each interval. And of course, if a rule like Simpson rule requires 3 points, then we would have an additional point in the middle of each of the subintervals defined by the grid. Equally spaced points, and then apply the rule on each subinterval. Note the points are placed exogenously here, so we have a control over where the points are, where the nodes are. And the accuracy of this approximation will obviously grow with the number of points. As we have more grid points, then the accuracy of the approximation of this integral will increase as well. But if we also choose to place the points exactly or optimally in some respect, we can ask the question, where can we put the nodes, the points where we calculate the function value to increase the accuracy of the approximation? Then we will arrive at the next approach, which is quadrature. But so far, this is how it looks, right? We have an interval from A to B, A here and B here. We have some nodes, and for every 3 nodes, we compute this approximating parabola and calculate the area under this parabola. And same thing here, or integrate this parabola. This is the approximation of the next 3 points. The next 3 points give us this. So here's the Simpson rule applied to the grid of how many points? 7. Right. Okay, that's what I wanted to say about this approach, and switch next to the quadrature approximation. And quadrature takes this idea a little bit further. So the idea here is that the integral also will be represented as a weighted sum, similar to all the Newton codes formulas. But now xi's and this omega i's, the weights, they will be calculated endogenously. So similar to the Chebyshev polynomial approximation, we want to find these nodes, the points where we want to calculate the function, such that the error of the computed integral is minimized. And quite spectacularly, you can have this result here, that the integral of the function of interest multiplied by the weighting function is exactly equal to this formula, where the main component, the sum of the weighted average of this function, of this functional values, is the dominating component. And this one, see, it has 2n factorial in the denominator, so it approaches 0 quite fast as n goes higher. This describes the procedure, the Gaussian quadrature procedure. With the key thing is that if f of x is a smooth function, and it has 2n of continuous derivatives on AB, then this formula holds, right? And the bottom line of this whole procedure is that we can, with n points, okay, n comes from here. So and enters this this summation. So with n points on x, which are placed accurately as the roots of this collection of orthogonal polynomials, with n points, we can exactly integrate any polynomial of degree 2n minus 1. And think about that. So if our function of interest is smooth enough so that it is fairly well approximated by a polynomial of degree 2n minus 1, then we can exactly integrate it with only n points in the given interval. And this is the power of the quadrature approach. Now, what follows is that I will just go through the theory or several theoretical setups of different types of Gaussian quadratures, where the weighting function and the quadrature nodes, the points xi's, are calculated differently. And in practice, we don't have to do that. We just have to choose one from the menu of these Gaussian quadratures that suits us best from some points, from some standpoint, and then just use that in the numerical implementation. And so let me go through this list and leave the practical exercise from for the next video where we will actually implement it. So first on the list is the Gauss-Chebyshev quadrature based on the Chebyshev polynomial. So the weighting function will be a familiar weighting function from the Chebyshev. The domain is also familiar. These different quadratures are defined over different domains and have different weighting functions. But here's the main formula. So the integral of the f of x of interest multiplied with the corresponding weighting function is given by the sum, and then we can disregard this error or correction coefficient because it is very small. The quadrature nodes are given by a formula here, but a lot of the times they're just tabulated, and we essentially we don't really have to calculate them. We're just using some already made numerical function. So here's an example of how to use the Chebyshev Gauss-Chebyshev quadrature. So imagine that we want to integrate f of x on a and b, and we don't have any weighting function. Yeah, where does the weighting function come from? Well, here we go. So first step, we perform the change of variable so that we take the problem from the interval a to b to the interval -1 to 1. And then we just multiply and divide by the needed weighting function. So it's going to go like this. We have the integral from a to b of our function of interest. We perform the change of variable, right? So we transfer the integral to the to the y variable, where y is given by this formula here. We get a coefficient outside of the integral, and we are now calculating the f of this expression. And then we just divide and multiply with the weighting function. Now this is the weighting function in the Chebyshev. So now we can think of this as our function of interest. Okay, and this is just going to be entering the formula for the Gauss-Chebyshev quadrature. And there we go. So we get a pi over 2 out as well. And now the sum, and we have this as the function of interest and the remainder of the weighting. And so this can be calculated in endpoints yi, which are the Gauss-Chebyshev nodes over -1 to 1. And as I said, this will be available through a standard function or a table. And then perform the summation. And that's all we need to do to calculate this integral. Now, Gauss-Legendre quadrature is built in the same way in principle. So it's a weighted sum of the function of values with some weights omega. But it works on the domain of -1 to 1. And the weighting function is just unity. So there is no weighting function here in the integral that we have to take care of. And in that respect, it's more convenient, right? So we just integrate the function we have to calculate or to find somewhere, and the values are tabulated, or in Python they're just available from the library function. We need this quadrature weights and quadrature weights, the omegas and the quadrature points, and we just calculate the function at some points and then calculate the weighted sum. And disregard this error term, right, as something really small. Okay, in Gauss-Hermite quadrature, the domain is from minus infinity to plus infinity, and look at the value function, the weighting function. The weighting function is the expectation of negative x squared. So for those of you who remember statistics, that looks a lot like the kernel of the normal distribution, right? Like the PDF of the normal distribution. So this is really convenient. Oh, by the way, this integral, the limits of integrations are on. They must be from minus infinity to plus infinity. Let's correct that. Inf t. Right. We can imagine that we have to calculate the expectation of this f of x, where x is distributed normally, or a linear function of f, something like that, or a linear function of x. Then we can do a change of variable and have the normal density in here, and then this becomes very convenient for calculation of this expectations with normal distribution. Values are again tabulated. Values for the quadrature points and the quadrature weights that we would use here. In Gauss-Laguerre quadrature, the domain is from 0 to plus infinity. And again, I have a typo. From 0 to plus infinity. The weighting function is the exponent of minus x. The weights and the quadrature points are again tabulated. So, let's think about the distribution that resembles this x of minus x, and that's an exponential discounting, right? That is useful. That might be useful with this weighting function, for which this weighting function might be useful. Okay, so as you can see, we have a menu of different quadratures, and we can basically choose from those which are useful for us. And Legendre is probably the most useful in the sense that it's a closed interval, and it doesn't require any additional value weighting function. And indeed, we will see how this is used in the stochastic consumption savings problem later on. Okay, so for the multidimensional case, quadrature can be generalized to the multidimensional case in a quite straightforward way. So if we have a function which has to be integrated on a hypercube of some limits in the number of dimension d, then we have essentially d different sums, and we evaluate the function at all the combinations of the quadrature points, and we multiply or weight with the product of the quadrature weights. And you can see that this can work for second or third dimension, d equals 1, 2, or 3. But then the number of points that we need to calculate this quadrature is a power function, right? So it's the number of points in one dimension or it's the product of the number of points in each dimension. So we have a power d here, and that leads to the curse of dimensionality, right? So if we have a really large dimensional space, then computing the quadrature in that large dimensional space becomes really computationally costly, because we need to evaluate the function so many times. So to help with that, you can think of some sparse methods, which basically replaces the full, all the points that are combinations of all different quadrature points by some agreed with sparsity. Only some points are used in this multidimensional cube. Or we can go to Monte Carlo integration, which is not subject to the curse of dimensionality in this sense. So let's look at Monte Carlo integration now. This is a stochastic algorithm for computing integrals, so it's based. Stochastic means that it's based on some random draws. The main idea is to approximate the expectation as a function with an average computed from the sample of random draws. So because the expectation of a function is an integral in itself, right, and we can approximate the averages by just drawing random numbers, having the law of large numbers on our side to ensure convergence, of the sample average to the theoretical average. And then because the theoretical average is an integral, then we can make that link. So so then we convert the integral in expectation to the integral that we are interested in. Let's see how it works. So what's happening here? Imagine that, well, first, before we go into the Monte Carlo integration, let's look at the expectation of the function of random variable. So if we have a random variable x with a tilde, so tilde everywhere denotes something which is random, and it has a PDF function, the probability density function p of x, over some domain omega, and imagine that we're interested in the expectation of the function of this random variable. Of course, the function of random variable becomes a random variable itself, right? Because it may take different values. And so this expectation of the function of the random variable is a well-defined object, and it's given by the integral, where we're integrating instead of x, we integrate an f of x, according to the distribution of x, and if x tilde is continuous, then we have this integral, where together with the function we also have the PDF. So you can see how it starts resembling the quadrature weighting functions. The variance is given by the standard formula, where the random variable x tilde now becomes f of x tilde. Okay, now let's see if we are interested in the integral, a definite integral over some set omega, and so I'm going to write omega instead of some limits of integration because we know that this is going to be useful in multiple dimensions. So omega is some hypercube, maybe some complicated shape in multiple dimensions, and we want to calculate the integral of f of x over that set. So here's the idea. Step 1. We can represent the integral as an expectation of a function of some random variable, okay? And here we can choose the random variable that we use to calculate the expectation of, or to calculate the function of which, right? Okay, here we go. The integral that we're interested in, it's written like that. Now imagine that we divide and multiply by some probability density function, okay? And then look at this expression here. And that's exactly the same as what we had here, except now instead of f, we have that fraction of f divided by p. And well, you know, just by definition, this is the expectation of this ratio of f to p. That's what it is, right? And so we can calculate this expectation using Monte Carlo. And then that expectation would actually be equal to the integral that we were interested in the very beginning. So that's step 2. We compute the expectation using n independent draws of xi from this variable from the distribution which is given by p of x. And so this approximation works because of the law of large numbers, which ensures this convergence. So as we draw more and more points, right, points xi's, then this average here is converging to the integral that we want to compute, because the integral is is equal to that expectation. Okay. So the simple case, okay, which actually corresponds to what we did in the previous video to approximate pi with Monte Carlo. In the simplest case, we can use the uniform distribution over omega, okay, and that makes this PDF p of x independent of x, right? So if a random variable x is distributed uniformly over omega, then we just need the measure of that set. And the inverse of that value to get the PDF. And as you can see, it's just flat. It doesn't depend on x. So if omega is an integral, for example, say between a and b, then this measure of that set is going to be just b minus a, and we would divide by b minus a over here. And so plugging this function in to the previous expressions for the integral, we have this, right? We have now this is just a constant. Let's compare. We had to divide with the PDF of the x tilde. Now we divide by this. That's the same as multiplying by v, and then we had to divide over here as well. Over here in the sum. And so now by dividing, we just multiply with v on the outside, and we can take it out because it now doesn't depend on x. Right. So why can we do this? Well, we are interested in the integral of a function over a particular set omega, but we have full control over what sort of random variable are we using to represent this integral as an expectation. Right? So we want to represent the function, the integral of this function using some random variable, and we have full control about over which random variable we're using. And so in here, we're just using the uniform random variable. Okay, here's an even simpler example. Imagine that we want the integral on the hypercube, and not just any hypercube. It's a unit hypercube. So it's a hypercube with the length of 1 on each of its sides, essentially, right? Each edge of this hypercube is of length 1 in n dimension. Then the value is also, the volume, the hypervolume of this cube is just 1. And that means that v vanishes from everywhere. And now the integral on this unitary hypercube is just an average, right? Or can be approximated by just average of the functional values. But remember now that this xi's, they are a random set of points uniformly distributed over the hypercube. That's important. Let's look at one-dimensional example to make it absolutely clear and easy. So if our omega is just an interval of r, just an interval in one dimension, then this v, the measure of the set, is just the distance, or length, should I say, b minus a. And now we are calculating the integral, a one-dimensional integral between a and b, and that can be approximated with b minus a over n, and then the sum, or b minus a times the average functional value. And here's a nice graphical representation of this process. So, if we are given the function which is a funny shape, and then we randomly take some points, we take a sample of points that belong to the interval a and b, and we generate these realizations from the uniform distribution on a and b, and then we are looking at the areas, under each of these computed function values. Why is it the area? Well, because we are multiplying by b minus a on the outside every time. And then we take an average, right? So it's an average of these areas, which are random because we are randomly generating axes. And so that approximately equals the integral, just because these are random points. Okay, so with all these ideas and theory in our baggage, here's the integral, the algorithm. So first we need to sample or simulate a large number n points from the distribution with p, where p accesses the PDF. And then we need to approximate the expectation of the ratio of our function to this PDF using the random draws and then sample average, right? So the integral that we're interested in is just going to be an average over the function that is represented by this ratio calculated in all of the random points. And let's call that QF of n. All right, with naive approach, which is the same as saying that we're using the uniformly distributed random variable on omega, we have the v, but we don't have the ratio, right? So we're not calculating the ratio of our function to some PDF. It's just the values of the function of interest that we are calculating here. All right, and so here's a simple realization on the multidimensional unit cube. Okay, so this is that simple case, just to illustrate some calculations. So what happens here? The inputs are the function, the number of dimensions for this hypercube, and the number of Monte Carlo draws that we want to use to calculate or to approximate the integral. So first of all, we need to draw random realizations from the uniform distribution, and we're using uniform distribution here. How many points do we need? Well, we're going to have n, capital N, of multidimensional points, and I'm generating here each coordinate of those points and placing coordinates in the columns of this matrix, right, by reshaping. So we have n dims times n random numbers, and we are making a matrix out of them. Then we're calculating the function. Well, this is assuming that the function can take a matrix as an input, and we'll treat the columns as the individual variables. Then the function should return n numbers, right? So y is going to be a vector of n elements. And then we just have to take the mean of y when we're using NumPy statistical functions here. And then the standard deviation of y divided by the square root of n will give us the standard error of the sample average. We will look in a second on what that is, and we'll return both. So let's repeat the pi example from the previous video by doing the following, calculating the following integral. So imagine that we have a function g, which is a function of two variables, and so it's going to be x0 and x1. But just to make it vectorizable, we will allow for the second dimension, right, by placing these dots in here. And what does this function do? Well, it calculates the distance to the origin. So it calculates the absolute value of each vector given by these two coordinates, and then compares it to 1. So this is an indicator function, in fact, and it indicates whether the point randomly drawn on the unit square, so unit hypercube in 2 dimensions, so whether that point falls within the radius 1 of the circle. Okay, so essentially we're doing the same exercise as in the previous video to calculate pi. So then we can call our function that we just written, and we multiply by 4 to get the approximation for pi, and then also we can calculate the standard error of this calculation of this estimate. Somehow a NumPy is not imported. That's not good. Let me go back in my slides and import NumPy and everything that goes with it. Oh, all right. We should probably do it here. So here we go. Let me rerun that and calculate the example again. So what do we have here? The number of Monte Carlo samples, so draws, is 1,000. The approximation of pi is 314.4. So the error is in the third digit. And we also have that the standard error, and we can actually see that, you know, this is much less than a standard error away from the actual value. So standard error is useful to give us an approximate, or to give us an idea of how far off we might have been with this Monte Carlo. Let's try to reduce the error. So the error is now in the third digit. If I use 10 more points, the error is still in the third digit. And if I use 100 more points, the error is still in the third digit. How about 1,000 more points? Oh no. See, we need a lot more points to get an error into the fourth digit. And this is the problem with Monte Carlo. In order to produce an accurate answer, it requires a lot of draws, right? So the standard error here is not reducing too fast. Well, how do we know that? Well, because we are essentially, when calculating the integral with Monte Carlo integration, what we're doing is we are approximating some average, some expectation using the sample average. And, we can use laws of statistics and the theory of probabilities to make statements about how fast the sample average converges to the actual expectation. And so here we go. The Monte Carlo integral as an estimator is consistent. It converges to the true value. So the limit of the sample average as the number of draws increases or approaches infinity is the expectation, which is the integral that we want to calculate. Moreover, it's asymptotically normal, so asymptotic normality holds. The difference between the Monte Carlo integral and the true integral is distributed normally, properly weighted or scaled. And so we can say that the standard error of our Monte Carlo integral is given by this expression here, sigma over square root of n, where n is the number of Monte Carlo draws. Now we don't know sigma as is usually in this statistical problem, and so we can estimate it with an unbiased estimator as well. Here's the formula for the unbiased estimator for sigma square, and this has a hat now that it's an estimator, and we can use this estimator to estimate the standard error of our mean. Of the estimator for the expectation, which is the integral that we want, right? And that's how we get the standard error of the integral itself. It's just that standard error divided by square root of n. And if we go back to the code, that's exactly how we calculated that. Okay, all these theoretical properties can also be tested by just running an additional set of Monte Carlo experiments that we do over here. But before going there, let's just note that the standard error of this Monte Carlo integral is given by exactly sigma over square root of n, or it can be estimated using the estimate for sigma over square root of n. And we can see that this standard error decreases with the rate of square root of n. And what does it mean? Well, it means that in order to double the precision of the estimate, we need 4 times as many random points. That's what we just saw. It was even worse, but of course this is a random realization, so it holds on average. But that tells us that Monte Carlo integral is not very precise. In order to increase precision, we need a lot of random draws. But what's the beauty of it? Can you see the number of dimensions anywhere here? It is independent of the dimensionality of the integral. So this omega can be really complicated and high-dimensional set, and still the error of the Monte Carlo integral decreases with the square root of n. And so that's what makes the Monte Carlo integration useful in multiple dimensions. This is a bit of a code that essentially just collects the estimates and the standard errors in a large number, like 1,000 of different runs to calculate the integral that we just calculated to approximate pi, and then draws a histogram. And because of the what's wrong here? And because we have asymptotic normality, PLT hist. There we go. because we have asymptotic normality, then we would expect to see something like a normal distribution here. A normal distribution centered around the actual pi, because the estimator is unbiased and consistent. So if I increase the number of runs, yeah, that's how we converge to a normal distribution here. And another thing to check is here's some text output. So the true value of pi is 314.15, right? The average is 314.10, so we are making a mistake in the fourth digit here. Now, this is an average of many Monte Carlo runs. Each Monte Carlo requires 100 random draws, and we're doing 10,000 of the Monte Carlo runs. This is averaging across the Monte Carlo runs, and therefore the error is sort of averaging out to give us even a more precise number here. But this is not what you would do in practice, right? You would just use a large number of Monte Carlo draws. With this exercise, we're studying the properties of the estimator itself. And so here's the mean bias. The mean bias is the average error that we're making, right? And the average standard error across all of the runs on the estimator. So these are the averages of this SE standard errors produced by the produced from the asymptotic normality considerations of the estimator. We can compare that to the average bias, or rather standard deviation of the bias across all of this runs, across all of 10,000 runs. And so across the runs, we can just measure, how much off we were in each run and what is the distribution of these biases. And we can then ask ourselves: is our estimation of this bias given by the standard error of the possible bias, is that a good number? And yeah, it turns out to be these two large numbers are really close. So when we are calculating the standard error of the Monte Carlo integral, that actually gives us a pretty good idea of how much off we might be from the true value. So okay, so this last bit was a bit of statistics that helps us to put in some error bounds on these things that we calculate in computational economics. But the bottom line is that quadrature integration is good for lower dimensional integrals, and Monte Carlo integration is more useful where you have a lot of dimensions to integrate over. All right, so there are some additional learning resources documents. There is a very nice tutorial on Monte Carlo integrations if you'd like more details, because I just sort of scratched the surface there. You can ask yourself a question: which distributions for the random variables should we use to minimize the standard error of our estimator? That's a very good question. And there's also, here's a link to a very useful library that we're not using, but you might want to consider using if you're doing a lot of Monte Carlos in your own work. All right, see you next time.